Hello everyone, and welcome to the sixth in the series Bite-Sized Training for All as part of the celebration of 50 years of the Protection of Wrecks Act. I'm Peter Knott, Education Manager of the Nautical Archaeology Society. Today's webinar is Which Marine Geophysics is Right for the Site? The presenter today is Mark James from MSDS Marine and Heritage.
Good evening, everyone, and thank you very much for having me, Peter. It's a pleasure to be here. I'm just going to stop my video. There we go. So before we start, I thought it might be useful just to introduce myself for those of you who don't know me, and to hopefully illustrate what makes me the person who is sat here talking to you about this subject. So I'm Mark James. I'm one of the directors at MSDS Marine. I'm also the geophysical lead for the company. I've always been fascinated by the subject, and if I'm honest, I'm a bit of a data nerd, which is good because I process and review thousands of line kilometers of data a year, mainly prior to large offshore developments. I also work in the field collecting data whenever I can, especially over protected wrecks, and I've done a fair few of the ones in the UK. I've also recently just come back from 3 weeks working with Drassam, surveyed a large number of the wrecks involved in Operation Dynamo. So this evening is intended to be bite-sized snippets of training aimed at giving you some useful tools and knowledge to start developing your own project proposals and to help you with understanding marine geophysics and which technique may be needed or useful for your site. Because it's bite-sized, there won't be time to go into every technique and every piece of equipment that's out there, but hopefully I'll be able to give you a few ideas of where to get started. With this year marking the 50th anniversary of the Protection of Wrecks Act, it seemed like a great opportunity to help people understand a little more about how marine geophysics can aid site management and our understanding of sites. So some topics may be familiar to some of you, but hopefully there'll be something both new and of use to everyone watching. So tonight I'm going to cover what is marine geophysics, including the type of equipment we use, how data is collected, the limitations of the techniques, and things you need to consider when planning your survey. We'll look at applications in marine archaeology through a couple of case studies, and then hopefully there'll be some time for some questions. Ultimately, though, it is a starting point, and I'm always more than happy to provide advice and to even comment on survey specifications you might plan, and even to look at data you might generate. As I said, I love data. A quick Google search will give you a lot of definitions of geophysical survey, and a combination of some of these definitions can give you something like what's on the screen. It's important to note that one technique, multi-beam bathymetry, is often referred to as hydrography, and there are 2 separate disciplines. One of these is geophysics and the other is hydrography. These techniques aren't specifically archaeological, and the use in technology is largely derived from oil and gas exploration, earth sciences, and bathymetric surveys for charting. Each category is a range of equipment, specifications, limitations, and costs, which all must be taken into consideration when creating a survey specification or commissioning work. These are the 4 most common. We have side scan sonar, multi-beam bathymetry, sub-bottom profiler, and magnetometer. So we'll start with side scan sonar. It uses sound, as do a number of these techniques, to produce a 2-dimensional image of the seabed. So it's a fairly straightforward concept. Sound waves are emitted from transducers on the side of a towed sensor, and then the intensity of the reflection from the seabed back to the instrument is recorded, and then this is presented as an image. So whilst working all on the same principle, there are a huge variety of sensors of various specifications, frequencies, etc. These can start from a couple of £1,000 for one attached to a boat chart plotter, through to professional grade systems which cost in the tens of thousands. A common budget system is the Tritech Starfish, which is just this one here, which can either be towed or hole mounted, and this costs between £3,000 and £4,000. This is an example of a more survey grade one, and these are transducers that can even be fitted to things like remotely operated vehicles. The one common specification that you will always see on side scan is frequency. For general survey and prospection, 400 to 500 kilohertz is usual. For high resolution surveys of a single site, maybe where you've got your shipwreck and you want to understand it in much greater detail, something like 900 kilohertz will give you better detail, but you'll have less range. So very, very briefly, the lower the frequency, the lower the resolution, but the greater the range. The higher the frequency, the better the resolution, but the shorter the range. One thing to always note, though, is take manufacturers' data examples with a pinch of salt. They put some beautiful images out there, but they're generally collected in very, very ideal conditions. So this is just an example of data collected at 300 kilohertz. So we can see the wreck, but it's limited in detail. And this is collected on the same line, in fact, at the same time, and this is at 900 kilohertz. We have our wreck, we have a lot more detail, but what you can see is that the overall range of the data collected is less. So it's a trade-off. Then also things like the distance of the towfish from the seabed and the distance from the feature can make a difference. So this is 700 kilohertz data, but it's collected very close to the seabed. But we can start to see an awful lot of detail with timbers here and the outline of the hull. So when thinking about doing a survey, line spacing is one of the key considerations. If you have, for example, a 100-meter range each side, then you're going to want less than 100-meter line spacing to achieve full coverage of the seabed. And this includes the water column here, where there is no data. So we need to make sure that we overlap this. Now, this section here will get wider the deeper the water is, or sorry, the further away from the seabed the sensor is. And when planning surveys, it doesn't matter how good the skipper is, they will never be able to drive a survey line exactly. So this needs to be accounted for in any movements to either side they may make. Very briefly, if we're searching a large area, then we want to collect data in parallel overlapping lines. If we're surveying a wreck, then it's lines along each side of the site and then across the top as well to get as much data over it as we can. So side scan is very useful for identifying very small objects on the seabed or getting a lot of detail about wrecks or covering big areas. It's one of the more accessible techniques out there, and it's now a common feature on quite a few recreational chart plotters. Whilst there are limitations in the quality of the data from these systems and also the depth you can use it in, it can be a very useful budget tool. Multi-beam bathymetry is definitely one of the more complex techniques and typically outside the scope of the recreational user. However, there are one or two systems available that are more towards the recreational end, if you like. Again, it uses sound waves, but this time the sound waves come from above, and the time it takes for the sound to travel from the sensor to the seabed and back again is used to calculate the depth. With each beam, and there can be a large number of beams, it calculates the depth, and this is stored as a point, and all the points together create a three-dimensional point cloud. So systems such as the WASP, these are probably the cheapest and simplest, and this is kind of the cheaper end of the multi-beam, if you like, but this is still going to set you back around £30,000. But when compared to the cost upwards of 100, 200, 300,000 pounds, it's considered cheap. I won't go through everything on this slide, but there are a number of factors that can affect the resolution or detail of multi-beam data. Some are hardware limitations, such as the number of beams, the frequency that is available, and the beam width. Some are adjustments that can be made during the survey, such as the swath width, the vessel speed, and again, the frequency. We can change the frequency on a lot of these systems. And then some are environmental, such as water depth. I mentioned that each beam recorded the depth, and this is how the data is output. So we have depth along with the position of that point in the real world. So this can then be imported into software that presents the data as a three-dimensional point cloud. We can also then grid this surface, this data to make a surface. But you can see here, this is each line, each ping of data, if you like, as the multi-beam's traveling along the water. So a few examples of how resolution and data density can affect what is able to be seen in the data. This is 1 point per 10 centimeters, and this is 1 point per 50 centimeters. So we can see here the details are actually quite good. So we can see a lot of features on this wreck here, and this is site 1 of the London for anyone who's interested. But then as we start to go to 50 centimeters, the detail starts to get blurry, it's fuzzy, we can't see so many of the features on the seabed. But sometimes lower resolution data or larger cell size can be good. So we can survey quicker because we can have our swath widths wider, and we can get really, really good ideas of seabed topography, which can help us in the management of sites. So we can see here, we've got a very deep dredge channel, and then this is shallowing up as we come away from here. And again, this is site 1 of the London and site 2 of the London wreck here. So we said side scan can identify very small things on the seabed. Multi-beam, when we're able to collect high enough resolution data, such as in shallow water, we can still see some of these small objects, but generally it's best for medium to large objects. But what's really nice is we can understand the seabed topography. So we can start to see areas of scour here, where material is actively moving away from a site, and we can see areas of accumulation where the seabed is piling up against the side of a site, if you like. So accumulation, we generally like, and scour, we tend not to. It's also a very useful tool for dive planning. If you've never been on the site before, we will know the maximum depth of the site is in the deepest part of the scour. It's incredibly good for looking at changes year on year. So we can see this is 2018, and we've got, this is the Roosevelt. We can see quite a lot of detail. So we can see some of the guns and some of the structure and the anchors that are here. But then in 2020, 2 years later, we can see that the sand has moved and much of the site is covered. So we can again use this to monitor sites and monitor changes to sites. We can make pretty pictures with it. This is particularly useful for public engagement and presentation, because this is a lot easier to understand than side scan sonar data for some people. We can use it to create really accurate and geo-referenced site plans. So the site plans will be where they are in the real world. So we can identify features such as guns and anchors and structure. And then we can use these to guide divers around if we're using acoustic tracking, or we can send divers off with this printed onto a slate so they can actually work out where they are on the site. So multi-beam can take a lot more time to set up and mobilize than other techniques, and it requires a bit more planning than other techniques. It's the one technique I'd always say it's worth seeking advice if you felt this was something that would be useful to a site that you're involved with. And we're always happy to help where we can on those things. I'm not going to talk too much about sub-bottom profilers. Its day-to-day use in relation to shipwrecks is fairly limited, although there are exceptions, and I'll give you an example. Unlike side scan and multi-beam, this is a technique that uses sound to view beneath the seabed rather than on top of it. And so it does this by using very, very low frequency sound waves, and they have the ability to travel past the surface of the seabed. And as they then go deeper and deeper, they reflect back to the sensor at different speeds, depending on the layers encountered. The lower the frequency, the greater the depth this sound wave will be able to travel to, but it also lowers the resolution. So again, it's the same trade-off between frequency and resolution and range. For shipwreck archaeology, we tend to use parametric systems. They just give us a really good balance of the depths that we need to achieve to visualize most parts of a buried shipwreck, but they also give us fairly good resolution. So just as an example, this is an example of sub-bottom profiler data, fairly low frequency, but we can use this to look at the paleo environment, so really, really old seabeds, and we have a channel here that we can see, which has now been infilled, and then we have the seabed running here. And then in relation to shipwrecks, again, this is site 2 of the London, and we can use it to start to identify the bottoms of bits of wreckage, or start to look at the extent. So we can start to see features showing up in the data here. So magnetometer is different again, and it doesn't use sound, and it's also a passive system, so it doesn't send anything out in the same way as the other techniques we've talked about. It also doesn't produce an image of the seabed, but what it does is detects changes in the Earth's magnetic field that have been caused by ferrous materials. Now, ferrous materials are those which contain iron. So again, there are different types for different uses and budgets. We have proton magnetometers, which typically made by a company called Aquascan, and they're a typical recreational wreck hunting tool. We have Overhauser, which is made by Marine Magnetics. Then we have cesium vapor. This is a geometrics one, which is more typical for the detection of unexploded ordnance. For archaeology, we certainly tend to use the Marine Magnetics one here. They're very good, very easy to deploy, and they're also fairly bomb-proof. Although they all use different technologies, they all detect changes in the Earth's magnetic field, but both geological and anthropogenic. Cheap ones may just show a reading on a dial, such as these ones here. Survey grade ones will record data including the strength, the depth, the altitude, and numerous other readings. Of all the sensors, magnetometry probably requires the most planning in relation to survey strategy, including the altitude, so the height above the seabed, and the line spacing. What is able to be detected will be very dependent on the distance of the object from the magnetometer and also the size of the object. So unlike the other sensors, there's no visual reference to help understand the coverage achieved. And because of this, the minimum object detection size will need to be thought about. Are you looking for an iron gun? Are you looking for a steel shipwreck? For a large steel shipwreck, this will be able to be detected from a much greater distance than a small iron gun. However, the position you have will only be where the magnetometer is, and the object may be some distance to the side. So for prospection of wrecks, wide line spacing may be able to be used to get the general location of a big steel wreck, but then we'd need to refine the line spacing and reduce it down to pinpoint the actual location. The data is exported as a text file, like we saw with multi-beam, but instead of depth, we have a position, which is just here, and then we have an amplitude. And it is the variation that will allow you to identify where it is detected ferrous material. So we put a baseline in, which is the background reading, if you like, and then we're left with what's called the residual. So we can see like minus 0.1 nanotesla and 0.1 nanotesla on this example. When we start to plot this as a graph, it becomes very, very obvious. And so we have our baseline here and we have an anomaly here. So we can see this is, say, minus 43 nanotesla right the way up to 80 nanotesla. So we know we've got something sizable here. Where we have enough lines of data and they're close enough together, we can interpolate it and we can grid it. And this gives a visual representation of where features are. So we can see we've got features here, 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 here. Okay, and we'll look at that as one of our case studies later on. So magnetometer can be a very accessible technique. And at one time it was a very common tool on many dive boats. And if you ask most dive boat skippers, they'll be able to give you countless examples of wrecks they have found using a proton magnetometer. So these are the Aquascan ones we're talking about. High detail surveys will require more expensive equipment. However, in most cases, they are fairly straightforward to operate. For a licensee or a recreational user, the vessel available will likely be a consideration in terms of what equipment to buy or hire. Whilst most boats are capable of towing a side scanner or a magnetometer, if you're working in deeper water, you may need equipment like a winch to bring the equipment back on board. And multi-beam, unless it's permanently fixed to the hull, it's going to require some sort of over-the-side mount. And these can be hard to fabricate or expensive to fabricate. So we're going to have a look at a couple of quick case studies. The first of which is Norman's Bay. It's a very shallow site, but it's also renowned for very poor visibility. And it primarily consists of iron guns and anchors on the seabed. Due to the shallowness of the site, multi-beam was seen as a very good option. Not only could we collect really high resolution data, it reduced the risk of towed equipment getting snagged. But to do this, we had to rig a frame up over the side of the boat to hold the equipment. The wreck and designated area were surveyed to understand the topography of the surrounding area and identify any features that may lie off the wreck. So this is the designated area, this is the wreck, and we made sure that we covered it. And for protected wreck licensees, it's always a good idea to survey the whole of your designated area because there may be material that lies away from the wreck. So zooming in on the site, we were able to make out individual guns. Here. We have an anchor here as well. And then we can use this data to to create very, very accurate site plans, effectively by tracing what we can see on the seabed. We can also identify features which are lying off the wreck, such as this gun here. We've got this feature over here. So when we did this survey, one of the things we did was georeference a hand-drawn site plan that was produced by Wessex Archaeology in 2007. This is a really interesting exercise for us to do because this site plan was drawn in using traditional survey techniques and in very, very poor visibility. But what's really, really interesting to note, and it's really nice for me to see as an archaeologist, is how good it actually is. So we can see that the majority of the guns are in the correct places. And the only thing we have sometimes is a slight difference in orientation, which is probably caused by using a compass to try and align guns in with a significant amount of iron about. It's not always the easiest thing to do. So the second case study is the Northumberland restoration. Now these are on the Goodwin Sands. The main aims of the survey were to understand the debris trail between the two sites, and the restoration's in two parts. So we wanted to see what was between those. We also needed to understand the maximum depth of wreck deposit that was potentially on the seabed. And then the Goodwin Sands, I'm sure many of you will know, is a highly dynamic area of seabed with huge sand waves that move very, very quickly. So we wanted to understand any potential future impacts that these moving sand waves may have on the sites. A lot of the material on the Northumberland restoration is iron. So we have guns and we have anchors and we have fittings and we have huge amounts of concretion on the sites from things like boxes of saber blades and things like this. So iron is always going to give us a very good indication of debris that may be between them. So because of this, we used a magnetometer to identify buried ferrous material that we might not see with the other techniques. Because we wanted to know the depth of deposit, we used a sub-bottom profiler, and then we used the multi-beam because we wanted to understand the topography and how the sand waves may be moving around the site. And all of this data would then help us assist us in updating the site plan. So we have the extent of the three data sets. The coverage of each was specified to meet the aim. So because we only needed to focus on small areas for some sensors, we just did that and we didn't expand it across the whole area. Sometimes it's possible to have too much data, so we just very, very much focused on what we needed. So we have magnetometer coverage here, we have multi-beam bathymetry coverage here, and then we have the sub-bottom profiler coverage here. Okay, so this is a really good image just showing just how quickly and substantially the sands on the Goodwin Sands move. And this is over a period of only 2 years, and it really highlights how at risk some of the sites on the sands actually are. So we can see here, these are to the same scale and they're using the same color scheme. So we have the Northumberland, which has sand all around it, and we have the restoration here. As we can see, in 2020, the Northumberland is now sitting just on the edge of a sandbank. And we also know from more recent data that it's right on the edge of the sandbank now, and this sand wave has disappeared. So potentially, once this sand has all moved away, the Northumberland's going to be sat on its own. And this is one of the reasons we wanted to understand the depths of deposit. But we can see from those images that the site is pretty at risk. So we can zoom in here on the Northumberland. Again, we've identified guns that we know are guns, and we've just highlighted them on the site plan. This gives us a very good visual reference year on year on how the site may be changing. So if more are becoming visible or they're starting to get buried. And then we have a similar one for the restoration. So again, we've marked the positions of guns and the anchors that we've confirmed and that we know are there. So the sub-bottom data was used to identify the amount of sand overlying the chalk surface below. And so you can see this matches up with the sand waves. So underneath we have the multi-beam bathymetry, and we've just given it a grayscale so that the sub-bottom data doesn't get lost. So we can see the edge of the sand wave here, and we can see that this is where the deepest deposit is here. So orangey red is around about 4 meters. And again, here we can see that we've got 0.3 meters, so between 20 and 30 centimeters of overlying sediment here, so not a lot really. But what we do know here is that we now have nearly 4 meters, or a potential of nearly 4 meters of wreck deposit should that wreck be sat on the hard surface below, which we believe it is. So the magnetometer data shows the wreck of the Northumberland, and then the two sections of the restoration. So we have Northumberland here, and we have restoration north, and then restoration south. So we can see both of these are characterized by fairly big magnetic anomalies. The more reddy pink it is, the greater the strength of the anomaly. But what it also shows is a large amount of ferrous material in between the sites. So we can see here and here, we've got bits out to the side. So this can really help us understand the wrecking event. But what it also does is allows us to define areas or targets that would be worth investigating when the site's next dived. So again, this is just a different way of displaying it. We've taken away the background, and we've got the multi-beam bathymetry underneath it, and we can see the areas of magnetic anomalies. So the range of geophysical survey equipment is large, and the appropriate tools should be investigated. And you can do this through using some of the information I've given you today, or just talking to us or other geophysicists. Everyone is generally very happy to help. The aims of the survey need to be considered. So what are we looking for? Do we need to understand small features that may be around the edge of the wrecks? Or do we need to understand the topography, the depth of deposit, and so on and so forth? You also need to understand limitations such as budgets. Survey planning is crucial to ensure that the data is fit for purpose. High-end equipment is specialist, and operation is often not straightforward. So if you need very, very high resolution surveys, then the appropriate specialists do need to be contacted. However, there are systems that are much cheaper and easy to use. The SciScan built into chart plotters, for example, or the Tritech Starfish. These are incredible pieces of equipment for the amount of money they cost. But don't forget, data always needs to be processed and interpreted. And again, in some instances, this takes specialist software to be able to do this, and then having to understand how to use the software. But again, there are a number of free versions of software about that will be able to do most things that you need to. For those of you working on protected wrecks, we're always really keen to help. A lot of our survey equipment is listed on the Protected Wreck Association members area, but I will always happily talk to anyone to provide advice and see how we can help. We do have a very good pool of geophysical equipment, and as I said, we are always very, very willing to help people, especially those working on protected wreck sites. So thank you very much for listening. I do hope it's been useful, and sorry it's a bit of a very quick run through. I've popped my email address on the screen here, and please do feel free to contact me for any further help and advice. I'm always happy to help in any way I can. Again, thank you very much for listening.
Thank you again, Mark, for your presentation today, and thank you, Historic England, for ensuring that these bite-sized webinars are free for everyone to attend and watch online whenever they like. If you're interested in project archives and working with curators and conservators, please tune in for our next bite-sized training webinar.